Welcome to another tutorial from Ada LLC. My name is Aladdin and I'm a senior engineer at Ada LLC, and in this video I'll be presenting our software FRP Buildings, the premium version 2.0. This software designs and analyzes concrete beams and concrete one-way slabs reinforced with FRP bars and FRP stirrups or ties as a direct replacement of steel. FRP building fulfills all the strength and the serviceability requirement from the guidelines. When you are using the ACI guideline, the software follows ACI318 and ACI440.1. When you are using the Canadian codes, the CSA, it will be following the CSA S806.12 and A23.3. These requirements consider the strength, the crack control, creep rupture, and deflection. FRP Buildings is designed by Ada LLC to create an easy way to design for FRP requirements in flexure and in shear, without the need for iteration. The software is easy to follow and very intuitive. The main interface is divided into two main sections. The left section is for the controllers and the right section will show all the interactive forms. The first step is to click Start and decide on the configuration of your problem or your design, which unit to be used and which code to be followed. The units is US units or SI units, and for the codes you can either use the ACI codes or the Canadian code. The next step is to define your materials, and you do this by click Material, the Material button, or click Next. In the material, you will be defining the concrete, the longitudinal FRP, and the transversal FRP. For the concrete, you will define the compressive strength F'(C), E-concrete, the modulus of elasticity of concrete, the modification factor for lightweight concrete, and the tensile strength FR, strain at maximum compressive stress known as Epsilon'(C), and the maximum compressive strain Epsilon'(Cu). You will be inputting all these numbers. Alternatively, you can only enter the compressive strength and ask the software to use the default value from ACI or CSA to calculate E-concrete, FR, Epsilon'(C), and Epsilon'(Cu). For the longitudinal FRP, you can use the user-specified option or our manufacturer list. Right now we have Tough Bar, and you will see a list of their product. You will click one of their bars, click Choose. You will see all the properties for the modulus of elasticity, for the tensile strain, for the bar diameter, for the material type. You click Choose and it will be reflected into the main interface. If you would like, you can use a user-specified option to define your own EF, the modulus of elasticity of FRP, the ultimate rupture strain, and the material type. For transversal FRP, you will be defining your material, the FRP, the transversal FRP, in the same fashion, either through a user-specified or our manufacturer list. And then you define the modulus of elasticity for the FRP, the ultimate rupture strain, and the material type. And then we have the exposure condition. ACI and CSA share the same exposure condition, just under different names. For the ACI, the first option is the concrete not exposed to earth and weather, and this is equivalent for interior exposure from the CSA. And the second option is concrete exposed to earth and weather, and this is equivalent to exterior exposure in CSA. The next option is to choose the geometry of the cross-section that you have. You can choose either a rectangular cross-section, a T-beam cross-section, or an inverted L cross-section. You will be inserting the width of the cross-section, and from the graphics you can see what do we mean by saying width, height, the whip width, the flange height, the side clear cover, which is necessary for a good distribution of FRP longitudinal bars, and the clear cover and the maximum aggregate size, which is also necessary for a good distribution of the bars. For the FRP properties, geometrical properties, you will be inserting the bar diameter, or you can use a bar number, like you can say number 4, number 5, number 6, and if you are using bar diameter you will be inserting 0.5 inches, or 0.625 inches, or it will be in millimeters if you are using SI units. In a similar way, you will define the transverse reinforcement, the tie bar diameter, or the tie bar number 3, number 4, or number 5. And then we have some geometrical limitation. The first value is KB, which defines the bond between the FRP and the surrounding concrete. This is a manufacturer values. It ranges between 0.8 and 1.4. 0.8 means a good bond between the concrete and the FRP. 1.4, it's not so good. And then we have the allowed crack width. So we allow a crack width of 0.028 inches. This value will be on this input will only be shown when you are using the ACI, since CSA is using the famous Z value way on deciding on the crack control design procedure. And then we have the permissible deflection. CSA and ACI shares the same exact allowed deflection between 4 cases. Case 1 is L over 180, and this is considering the deflection due to live load, the immediate live load, and it's to be useful for flat roofs not supporting or attached to non-structural elements likely to be damaged by large deflection. And then similarly, case 2, L over 360, case 3 and case 4, L over 100-240, for example, for case 4, and this is the sum of long-term deflection due to all sustained loads and the immediate deflection due to any additional live loads, and the software follows the same exact regulation when considering the deflection based on the case you choose. And then if you would like to use a different value and not including these cases, you can insert your own custom allowed deflection like 1 inch, 2 inch, or 25.4 millimeters, and so on. And then we have this checkbox for the high levels of sustained loads. This is, for example, for libraries when the books will be sustained for a very long time and it's a high level. This value or this checkbox is only appearing when you are using the ACI, since the ACI consider a big difference between when there is a high levels of sustained loads and when there is normal levels of sustained loads. And if you're using CSA, this checkbox will not be shown because the CSA does not distinguish between a high level of sustained loads and a normal levels of sustained loads. And then the next step is to define the beam configuration. We have two options: either choose from a predefined beams, and then in this case you will decide you will be using one of our beams from our internal library, or you define your own beam when you have a different loading condition or a different boundary condition. For the predefined beam, we have four options: either 1 span, 2 span, 3 span, or 4 span. If you click 1 span, for example, and click submit, you will see 4 loading condition with 4 different boundary condition: a cantilever with a concentrated on the tip, or a cantilever with a distributed load, a simply supported with a concentrated on the middle, or a simply supported with distributed load. You will also be defining the length of the span, and click submit. Before showing you the loading, I'd like to show you another example. If we choose a 4 span, for example, and click submit, there are 4 cases: a continuous when all the spans are loaded, when the first 2 is loaded, when the first and the third is loaded, and the second and the third is loaded. This is meant to capture the maximum positive and the maximum negative for different cases. You will also defining the lengths of all the span and which span to be analyzed, either span A, span B, span C, and span D. I will also would like to show you the custom beam or the custom values. When you don't have your condition, the boundary condition or the loading condition from our library, you can define your own beam based on defining number of sections. We have 2 options here. You can use the external deflection method or the 5 moments method. The external deflection method is completely accurate and depends on defining 3 sections: section 1, section 2, and section 3. Section 1 is the section just after the support from the left. Section 2 is the mid-span moment and the section 3 is the support, is at the right support, just before the right support. You will be defining the ultimate moment, the sustained moment, the service moment, the dead load moment, and the shear, the ultimate shear. In addition, you will be deciding, or you'll be calculating the uncracked maximum deflection under service load. So you will use the gross moment of inertia under the maximum positive service moment that you will be defining in section 2 to calculate the uncracked maximum deflection under service load. To calculate this deflection, you will be using an external software, structural software, to get this number. And our software, FRP Building, will use a rational relationship to build between this case and the actual case when the section is actually cracked, and we will calculate the strength and the deflection based on an accurate approach. You will be also defining the custom beam length. The second option is more approximate, but it's an easy and does not require the use of an external software, and you will be defining 5 sections. Section 1 and section 2 and section 3 are the same, but you will also be defining an additional section at L/4 from the left and a section at L/4 from the right. The software use this information to build an approximate solution for the deflection. You will also be inserting the custom beam length for the span that you are analyzing, or the beam that you are analyzing. You can see a complete deflection description of the cases. If you click on 5 moments method, you can see a complete description, and if you click at the external deflection method, you can also see a complete description of the method and how the software using a rational relationship to get an accurate deflection from the information or the data you input. The next step is to click submit. When you have, for example, a predefined, you click submit and you define the loading and the load combination that you want to use. We have all the load combination from ACI, and if you are using CSA, you will see all the load combination from CSA A23.3. You click one of the desired combination and you will input the live load directly in these text boxes. You can also ask the software to pick the critical combination for you. So the software will run a simulation for all these cases, for all these load combination, and get the maximum value and use it as a critical value. Or if you'd like to use a different approach and not using these combination, or if you are living in a country that does not follow ACI or CSA, you can insert directly the ultimate factor total load and the service total load and the sustained total load and the dead load using your own coefficients. If you are using 2-span, 3-span, and 4-span, and for example you are designing span B, you will be inserting, there is a dead load to be considered on the other span, and this is where you insert it. So there is an effect from the other span on the span that you are designing, and this dead load is will be including the self weight, and it's equally distributed over all the spans, and this is meant to capture the effect of the other span on the desired span. And then you simply click design. I'll be loading an actual design case that we have through the open and save option in the software. This is a very valuable to be organized and save all your inputs for future checking and design. So you click open, and then I have the file saved here. I'll double click it and the inputs were loaded successfully. Click OK. I'm using SI units with an ACI code. My material for concrete is 35 megapascal, and I'm asking the software to use the default value to calculate the rest of the concrete properties. I'm using a user specified option for EF and Epsilon FU with a glass rebar, and the same for the transversal FRP. My exposure condition is interior. I'm using a rectangular section with a B of 500 and a height of 600 millimeters, 25.4 side clear cover and 50.8 clear cover with a maximum aggregate size of 19 millimeters. For my longitudinal FRP, I'm using a 1 inch or 25.4 millimeter bar, and for the transverse I'm using 12.7 millimeter, and for my KB value is a good bond of 0.8, and my allowed crack width is 0.787, and for my deflection I'm using a custom allowed deflection with a high level of sustained load, and my value for the allowed deflection is 25.4 millimeters. For my beam configuration, I'm using a 4-span option with the case of the span B and span C are loaded. My lengths are, I have for the first span is 4 meters, for my second and third is 8 meters, and my fourth span is 4 meters, and I'm asking to analyze or design span B. I click submit, and my load combination is 1.2 dead and 1.6 live load of 29.19 and 29.2 for the dead and for the live, and then I click design. Since I have a continuous span, there will be 3 sections. If I have one span, for example, simply supported, there will only be 1 section. So for our case, the number of sections designed are 3, 1 on the left, the mid span 1 or the maximum positive 1, and 1 on the right. So the one at the left at the location of 0, which is starting from the left, measured from the left. My ultimate is 261 negative, of course. My service is 186. My sustained is 112. And the software is telling me to fulfill all the requirements, strength and the serviceability. I'll be needing 7 bars at the depth of 76.2 from the top of the section, and my controlling design or the design mode I have is deflection. For my second section, for flexural design, it's at 3.6 meters from the left with a 268 positive moment, ultimate moment, 191 for the service moment, and 114 for the sustained moment, and I need 8 FRP bars at a depth of 523.8, and of course the controlling design is deflection. And then the third section at the right is at 8 meters, which is at the end of the span, with a negative 523 for the ultimate, 373 for the service, and 224 of the sustained. And I'll be needing 2 layers, since 1 layer will not be enough to fit all the bars, and the software distribute the bars according to the code and the allowed spacing between the bars. For the first layer is 8 at a depth of 76.2, and the second layer I need 5 bars at 127, and the controlling design, of course, deflection. For the shear design, my first section is at D from the support, which is at 0.52 meters from the support, and the ultimate shear is 251, and the stirrup spacing required, I will be using my bar diameter that I inserted at 109 millimeters. At the maximum positive moment, this is a 0 shear moment. This is a 0 shear area, so no shear stirrups are required at that section. And for my the third section for shear design, the location is 7.5 meters measured from the left, which is toward the end of the span from the right, and the ultimate is negative 318.43 kilonewton, and the stirrup spacing required is 84 millimeters. I will also be seeing the ultimate bending moment, which reflect the same exact number for the ultimate moment that we just read from here. And then we have the ultimate shear diagram, positive at the left and negative on the right. The next step is simply to click report, and the software will generate a very detailed report including all the inputs, all the outputs, all the equation used, and all the limitation, with all the variables completely defined for the engineer checking and designing. You will simply click report, and you will save your report on the PC, and you can easily open it. So I will just save mine quickly. I'll say example 1 and save. The software will just take few seconds to generate the report, and then you can open it directly. And then I can open my report. And as you can see, this is the case name that we just named it, example 1. This is the date of today. And then this is the table of content, the objective of the design configuration, the sectional parameters, the material properties, the beam configuration, the loads, the structure analysis of the problem, the design procedure for flexural, and the shear design procedure, and then the final summary of results and the notations. The software reflect the philosophy of the report reflect the philosophy of the design that we used in the software. So we start with the objective, and then the design configuration, which units and which code that were used, and this is the sign convention. And then we have the sectional parameters for the cross section. We have a rectangle, 500 width and 600 height. And then for the reinforcement, we used 25.4 millimeters, and for the bar diameter, the tie bar diameter or the stirrups, we used 12.7 with a bond dependent coefficient of 0.8. And then for the material, we have a 35 megapascal for the F'(C). We have all the concrete and with all the equation that we used since we clicked the default values. And then for the FRP, we have the longitudinal FRP, EF, maximum tensile strain, material type, the exposure condition, and the same for the transverse FRP. And then for the beam configuration, this is the configuration that we chose. The length is 4884, and the analyzed span is B, and it's loaded. And then we have a load combination of dead load equal to 29.19 and live load at 29.19, and this is the load combination that we used from ACI. And then for the structure analysis part, we get the moments, all the moments, the ultimate sustained service, dead load, and the ultimate shear for the 3 sections that we have, and the location of this section, the 0 from the left, 3.6 for the maximum positive moment, and 8 at the right hand side of the span. And then we have the node rotation. This is for the structure analysis part. We have the ultimate bending diagram, and we have the shear diagram. And then we start our design procedure for FRP, the flexural FRP. We have allowed crack width of 0.787. This is the limitation, the design limitation. And our sustained stress for the creep rupture should not exceed 95.37. We have to fulfill the requirement for strength, and we should not exceed an allowed deflection of 25.4. For our material limitation, since we used glass with interior exposure, we have environmental coefficient of 0.8. This reduced our tensile strength to 476.8 and our epsilon FU to 0.011. These are the values we are going to use in our design, using these two equations, CE times the ultimate for the strain and for the stress. And then we have the gross sectional properties uncracked. We get the M cracking, we get the gross moment of inertia, we get YT and N, and these are the equations that we used. And then we have the cracked condition. So all our sections are cracked under service and under sustain. The first design mode is crack control, and the software designed for this mode. So the objective is that for the spacing between longitudinal FRP bars must not exceed the maximum spacing defined by the guidelines from ACI, or would be the Z value from the CSA, where the maximum and must not be less than the maximum of 1 inch 4/3 of the aggregate size or the bar diameter. So the software tells me at these 3 sections I will need this total area of FRP, at which depth, what's my M cracking, what's K, what's I cracking, what's my stress in this case in the FRP, what's beta, which is also shown in the equation, and the spacing and the maximum spacing allowed between the bars. And then the software and the report show you the creep rupture and they use this crack control first to get you a value. For example, if we need 3 bars to fulfill the crack control, when we design for creep rupture, the software start from 3 bars. We don't go for 1 bar or 2 bar design because it does not fulfill the crack control. So we build up on the design of the crack control, and then we go for the creep rupture and we see if we fulfill it. If not, we start increasing bars till we fulfill it. So we have the total area for the 3 sections, and we have the M cracking, we have the K, we have the I cracking, we have the highest stress, FRP highest stress, and the FRP stress limit for the creep rupture. And these are the limitation from the code. We have a limit of 0.2 FFU for glass, and 0.3 FFU for the aramid, and 0.55 for the carbon. And then for the strength requirement, we also build on the creep rupture and crack control, and we find what's the total area required, at what depth, what's my concrete strain at the maximum compressive fiber, what's my strain and FRP, what's beta 1, what's alpha, what's the balance ratio, and what's phi, the reduction factor or the reduction coefficient, and what's my nominal moment, and what's phi mn for each cross section, and what section, what strength mode control this strength design. For example, section 1 is controlled by FRP rupture, section 2 and section 3 are controlled by concrete crushing. Also, the software check against the minimum FRP area. So in case of concrete crushing, to check the minimum FRP area is not required by the code, so we only check the minimum FRP area for FRP rupture. The report then will present the concrete crushing failure mode equation and the FRP rupture failure mode equations. And then we have the deflection, the design for deflection, the length of each span, and what's the condition of the sustained loads, and then we have the member properties. Deflection is a property of the whole span, not each section by itself. So we have the property for the span, we have the effective moment of inertia under service load, I effective for the whole span, and the I effective under dead load for the whole span. We have the deflection under dead load, under service load, under sustained loads, under immediate live load, under unsustained loads, and then incremental for 3 months and incremental for 5 years, and the maximum deflection location measured from the left end of the span. And then we have the equation that we used, and then we have the properties of each section in the span for the deflection calculation. We have the cracking moment, IG, the gross moment of inertia, we have the cracking moment, and then we have the effective moment of inertia, IE, for each section that we used. We used these 3 to get the I effective for the whole span. We have the total area of FRP, at what depth, we have the service moment, and we have the dead load moment. And then we have the FRP shear design procedure, the location of the sections, and then we have the critical section VU, the ultimate shear, and the MU at that section, at the effective depth, the total area of FRP, and then VC, which is the concrete shear strength, and we have the VF, FRP stirrup shear strength, and we have the summation VN, and then we have K and FFV and FFB, the bend bar strength, and we have the area of FRP reinforcement in shear and stirrup spacing, and the maximum one, and then the final one. Right now, as was presented in the results, we need 109 on the left section and 84 millimeter spacing for the right section, and in the middle we don't need any shear reinforcement. And then we have all the equations that we used either for ACI or CSA. It will be shown in this location. We have the VU equations, we have VN equation, we have the minimum AV equations, and then we have VF equations and VC, and then the minimum AV, and then the final, the S-max, the maximum spacing. And then we have the final summary of results, section 1, section 2, and section 3. design mode was deflection. We need 7 bars in section 1, we need 8 bars in section 2, and we need 13 bars in section 3. This is the total area. These are the depth df for each section. For section 1 we only needed 1 layer of 7 bars. For section 2 we needed 8 bars in 1 layer, and section 3 we needed 2 layers. The first layer is 8, the second layer of 5 bars, and these are the areas in each layer in each section, and then these are the depth of each layer. And then for the sectional shear design we needed 109 millimeter spacing for section 1, no stirrups in section 2, and section 3 needed 84 millimeters spacing in section 3. These are the section 1, section 2, section 3 to scale. Everything is to scale for the stirrups, for the bars, and for the cross section. And then we have the notation. So every property or every parameter that we use in the report will be shown definition. The definition will be shown in the notation for all the equations and all the inputs and outputs. And then finally we have the disclaimer in the report from ADA LLC. FRP buildings present a very easy way to design for FRP requirements in flexure and in shear for concrete sections reinforced with FRP rebars in flexure and in shear. Either it was a rectangular section, T section, or inverted L section with a huge number, with a very large pool of boundary condition and loading parameters, with a very generalized approach through the 5-moment section and the 3-moment section with the deflection method. Thank you for listening, and please visit us at www.aeda.app if you have any questions or you would like to have your own version of FRP buildings.